All right, today we are tackling a really deep mystery, one that's kind of hidden in plain sight. It's a question about the very fabric of our physical world.
So let me ask you something. Could the water in your glass or the steam rising from your coffee just explode? I know, it sounds like something straight out of a sci-fi movie, right? But believe it or not, this is a question that has genuinely stumped the world's best mathematicians for more than 100 years. Can a perfectly calm liquid just spontaneously erupt into total chaos?
And, this isn't just some academic thought experiment. This is a huge deal. It's actually one of the 7 most important unsolved questions in all of mathematics. It's what's known as a Millennium Prize problem.
Yep, you heard that right. $1 million for anyone who can crack it with a formal proof. So, okay, let's dive in and see what this is all about.
So the heart of this entire mystery, it all comes down to a set of equations called the Navier-Stokes equations. Basically, these are the fundamental rules that tell fluids how to move. We're talking everything from the currents in the deep ocean to the air flowing over the wing of a 747.
And here's the big question. Do these flows always stay nice and smooth, or can they just spontaneously develop what are called singularities? We're talking points of infinite speed and infinite pressure. In other words, can a perfectly normal fluid, just following the rules, suddenly go totally haywire and blow up? I mean, obviously, in our everyday lives, this never happens. But the real challenge? Proving it can't mathematically.
Okay, so to get why your coffee doesn't just explode in your face, we need to bring in the hero of our story. It's a property called viscosity.
You can think of it as just a fluid's internal friction, its stickiness or thickness. So honey, super high viscosity. Water, pretty low. And this one property, this stickiness, it turns out to be absolutely crucial. I love this analogy. Think about whipping cream. No matter how fast or violently you whip it, it never explodes, right? It just gets thicker and more resistant. That's viscosity in action. The faster you try to move it, the more it literally pushes back. It's like a built-in brake system for fluids. So at the very heart of these equations, there's this epic battle going on. On one side, you've got vortex stretching. Let's call this our villain. Its whole goal is to amplify chaos, to twist the fluid into tinier, faster, angrier little swirls. And on the other side, we've got viscous dissipation. That's our hero. It's always trying to calm things down, to destroy the chaos and smooth everything out. So the million-dollar question is pretty simple. Who wins this fight?
All right, so to settle this fight once and for all, mathematicians needed a way to keep score. They needed a single number, like a scoreboard, that could measure the total amount of chaos, the twistedness, in a fluid at any given moment.
And that number has a fantastic name, entropy. It's just a perfect word for it, right? A higher entropy score means you've got way more intense, tiny, chaotic little whirlpools or vortices churning around in the flow. And this is the key. For a fluid to actually blow up, its entropy wouldn't just get big, it would have to become infinite in a finite amount of time. So the whole question really boils down to this. Could our villain, vortex stretching, ever actually generate an infinite amount of this entropy?
So how in the world do you prove something like that? Well, the proof that a blowup is impossible isn't about solving one super complicated equation. No, it's much more elegant than that. It comes from uncovering a brilliant and totally fatal logical contradiction.
Okay, let's walk through the logic here because it's awesome. First, the universe gives any fluid a finite amount of energy to start with. You don't get an infinite energy budget. Second, the math shows that this finite energy budget puts a hard absolute cap on the total amount of entropy the fluid can ever produce over its entire lifetime. But, and here's the kicker, a mathematical blowup would, by definition, require an infinite amount of entropy. See the problem? It's asking for an infinite resource from a finite budget. It's like trying to spend an infinite amount of money when you've only got $100 in your bank account. The math just says, nope, can't be done. It's impossible.
And this is where our hero, viscosity, really shines. This chart shows it perfectly. The higher the viscosity, the stickier the fluid, the faster it just crushes that chaotic entropy. Viscosity is basically the universe's enforcer. It's the mechanism that makes sure that finite energy budget is respected, and it guarantees the chaos can never ever spin out of control. Okay, so the math says it's impossible, but what's actually physically happening down inside the fluid that prevents this disaster? How does viscosity win this battle on the microscopic level? Well, it happens through this amazing process called an energy cascade. You see, big energetic swirls in a fluid, they don't stay big for long.
They break apart into smaller swirls, which then break apart into even smaller ones. All that chaotic energy just keeps tumbling downward, cascading to smaller and smaller microscopic scales. And when things get tiny enough, viscosity takes over completely. It creates something like a dissipation floor, a point where the chaos just can't get any smaller. Instead, viscosity steps in and transforms all that chaotic energy into something totally harmless: simple heat.
And that, right there, is the ultimate takeaway. The Navier-Stokes equations, they're really just a heat equation in disguise. All that wild, complex fluid motion is, at its very core, just a system for turning chaos into heat. And what does heat do? It smooths things out, it spreads, it never, ever concentrates into a single, infinitely hot point. So thanks to viscosity, fluids are fundamentally self-smoothing. They are self-regulating systems that can't blow themselves up.
It's a really profound idea when you think about it. This isn't just about water in a glass or air over a wing. It shows that deep within the mathematics that describe our reality, there are these beautiful, elegant safety nets built right in. They are fundamental principles that keep our universe predictable and stable, and ultimately safe from its own most chaotic possibilities. It really makes you wonder, doesn't it? What other fundamental laws are out there, quietly ensuring our universe doesn't just spiral into chaos?